Welcome to another video. Basically, this is the continuation of discussion on non-Newtonian fluid flow in a circular conduit. So here what we'll be talking is pressure drop. Okay, so now we'll have to recollect actually see what we have done in case of Newtonian fluid analysis. First of all, we have been having one expression delta P by into R by twice L as a tau R x. Okay, because of x velocity at any location R, this is the magnitude of the shear stress. So now wall shear means actually see this R is equal to radius of the tube. Okay, so then therefore wall shear is equal to delta P into R divided by 2L. Now there we have found that actually the wall shear rate is 8 times, this is 8 times of V average by D, and this is mu. Okay, so now this is for Newtonian fluid. Now you can recollect actually this shear stress is equal to mu multiplied by wall shear rate. Now you see we are now talking about this non-Newtonian fluid. So what we will be expecting is that actually see we are interested to have again wall shear and again you see wall shear rate, but here this power should be coming as n, and then what should be the equivalent term for this mu? So that is actually you see there is nothing called mu in case of non-Newtonian fluid. We have got k and n. So whether can we just directly use k here, or it should be a k multiplied by some more things into it. Okay, that we are going to see. So mu is not applicable in case of non-Newtonian fluid. Now another is that actually it should be a power law fluid. So now based on this equation we will be applying this equation. Based on that equation, you see V average is equal to n by 3n plus 1 delta P by 2kl 1 by n and r to the power n plus 1 by n. Okay, so there we are substituting the value of V maximum. We are going to get this particular simplified expression. So then V average is n by 3n plus 1 by delta P by 2kl 1 by n r to the power n into r. Okay, so this is getting divided because we want to have a term delta P by R. Okay, so delta P by R, so that we can take out one of the term. Okay, here you note that this expression for V average we modify slightly. Basically this R we are breaking it down to r to the power 1 by n into r. Similarly this k is additional term as compared to this expression here. So now you see we are taking out this term from this side, so k had to remain separately. We took out k. So then delta PR by 2l to the power 1 by n is equal to 3n plus 1 by n. This got inverted. This V average divided by this r is coming to the denominator, and k to the power 1 by n was at the denominator, so it is coming as the numerator. So then delta P by r to the power, r divided by 2l is equal to, actually we took nth power for both these sides, then we get this expression 3n plus 1 by n to the power n and V average by n to the power n, V average by r to the power n. Okay, so then what is it? It is wall shear here expression, that is equal to, now is k to the k multiplied by, we are doing some modification. It is not 8 times as of now. Okay, so we are doing modification here. You just see k 3n plus 1 by 4n. Now this r is basically see half d, so we are multiplying it 2 here. Therefore actually we are means multiplying 2 at the numerator as well. 2r twice V average. Again here we are multiplying in the denominator another 4, of course with the power n. So similarly here also we will be multiplying with 4 to the power n. So 2 coming from here and 4 coming from here, it becomes 8 to the power n. So 8 V average by D to the power n. then you see, let us see our expectation that this is equal to some coefficient multiplied by this shear rate to the power n. So we can see here, you see, 8 times of wall shear, means this is actually wall shear to the power n is there, and left hand side it is delta p into r by 2l, which is the wall shear stress, and this is the shear rate, and this is the coefficient which is equivalent to this mu. So k multiplied by 3n plus 1 divided by 4n, and this particular factor to the power n, that is the now k prime we are saying. So here k prime is equal to k multiplied by 3n plus 1 divided by 4n to the power n. So now this needs to be something equivalent to viscosity. So now let us recollect for Newtonian fluid that tau w is equal to mu is equal to minus dv by dr to the at the wall. So then when we substitute, and you can recollect that we are saying that wall shear rate is equal to 8 times of V average by D, and then we got this expression, you see. Then what is mu? Mu is wall shear stress divided by wall shear rate. Wall shear stress divided by wall shear rate. Okay, so then mu is equal to wall shear stress divided by wall shear rate. Alright, so this is the equation we can use for estimation of viscosity in case of Newtonian fluid. So now, what will be the ratio of these two terms in case of non-Newtonian fluid? So tau w will be equal to now wall shear is k prime, just now we have seen in the previous page. Okay, k prime into minus dr to the power, not sorry, k prime, it is wall shear is equal to k prime, yeah, this prime is there, k prime minus dv dr, and that again you see at wall, this is shear at wall. So it means left hand side is delta p into r by 2l is equal to k prime into 8 times of V average by d to the power n, that we have already done. Since it was at wall, so this is the expression. So here we do not require to write w again. Okay, so then what we require is, you see, this ratio delta pr by 2l divided by this shear rate at wall. So this particular factor divided by, we are taking out only one of it. You see, to the power n is there, so we are taking only, you see, a factor of 1 out of it, so then it becomes n minus 1. So k prime into 8 times of V average by d to the power n minus 1. So now if you compare this equation 1 and this equation 2, you will be seeing that, okay, there is a term equivalent to mu. There is a term in non-Newtonian fluid flow equivalent to mu. So now let us call it as a mu prime. Okay, mu prime is equal to k prime into 8 to the power V average, 8 into V average by d to the power n minus 1. Okay, so this is equivalent of mu. Okay, so this we can take write slightly differently. You see, k prime into 8 to the power n minus 1 we can take out, and V average by d to the power n minus 1. Now this particular factor, this coefficient part of it, V average by d will be there to the power n minus 1, that will remain there. So k prime into 8 to the power n minus 1 is called the generalized coefficient of viscosity. So this is the notation used for. So generalized viscosity coefficient is the k prime into 8 to the power n minus 1. Again, you see, k prime is what? K multiplied by 3n plus 1 divided by, here it is, 3n plus 1 divided by 4n to the power, whole thing to the power n. Okay, so then this is the generalized viscosity coefficient. So after we know the generalized viscosity coefficient, then what is the expression for Reynolds number in case of non-Newtonian fluid? So in non-Newtonian fluid, in Newtonian fluid is what is rho v d by mu. So here we are going to give the expression for equivalent mu. So what is the equivalent mu? K prime multiplied by 8 into V average divided by d to the power n minus 1, and V average is there in the numerator also, hydraulic diameter, and of course for circular pipe it is equal to the actual diameter into rho. So numerator is not changing. So now this is the what we get after simplification. We get V average to the power n minus 2 minus n d to the power n and rho k prime a to the power n minus 1. Again, is this factor we have called as a generalized viscosity coefficient. You can recollect in the previous page we have said that okay, this is generalized coefficient of viscosity. Means actually see what is the Reynolds number then? Denominator is generalized coefficient of viscosity. Numerator is V average to the power 2 minus n and d to the power n and rho. Now you can compare it with your Newtonian fluid. If n is equal to 1, this factor becomes 1. This factor becomes d to the power 1, means V average into d into rho divided by, now this becomes mu. Okay, rho V d by mu, means viscosity coefficient. So this is generalized viscosity coefficient in case of non-Newtonian fluid, and in case of Newtonian fluid it will be viscosity coefficient. Then pressure drop, same formula we are using for AC. Theoretical expression we can get for only means laminar regime. So in case of laminar regime, what we get? F is equal to 16 by Reynolds number. In case of non-Newtonian fluid, it will be generalized Reynolds number. Okay, so then delta P will be 4FL by D rho V square by 2. So then you see this this term 4F will be basically 64 times of NRE generalized L by D into rho V square by 2. And so 64 mu V average to the power 2 V average to the power 2 minus n d to the power n rho, and L by D rho V average square by 2. So now this actually see, somebody may just see means simplify it, like you see, by cancelling out the terms, then it becomes 32 into this generalized coefficient of viscosity. But again, you see, generalized coefficient of viscosity has got this expression k prime to the power k prime into a to the power n minus 1. Okay, 32 into generalized coefficient of viscosity V average by D to the power n and into L by D. So this is the pressure drop. So for calculation of pressure drop in case of non-Newtonian fluid, we can approach in this way. You see, if we can estimate F here, and then we can actually see directly substitute in this particular equation. We can avoid coming to this complex means involving some new variables. So you just estimate F by this equation. However, there you will have to note that actually you are taking the generalized Reynolds number. So what is the generalized Reynolds number? This one. And then what is there in the denominator in case of generalized Reynolds number? It is generalized coefficient of viscosity. So what is the generalized coefficient of viscosity? It is k prime into a to the power n minus 1. Okay, so that's how actually this pressure drop can be calculated in case of non-Newtonian fluid.